morning, Jennifer. My hair's going crazy. How are you doing? Good to see you here on this Wednesday morning before class. Cameron, good morning. I'm just labeling a few of the videos. I'm so glad we had our special guest last class about study abroad. I think that went really awesome. So, chapter 16, more on tests again today in class. More on tests. Here we go. He's the thumbnail for the video. I guess I'll change it. I don't know. I'll send it. I'm gonna send it to her here and say like, here's your video in case you want. You might hear it in the background now.
Students, please.
Okay. And these are great too. You get to go.
Oh, it turned out so good with the audio. I was going to start the quiz early, but we didn't go over type 1, type 2 stuff. Rip. Oh no. Here, I'm gonna send this over. Say, here we go. Thank you again for visiting. Here is the video for rap. There we go. I just learned it from old videos. Oh, you took it from the old videos about type 1 error, the null is true, type 2 error, the null is false, and we failed to reject it. William's just going ahead. William, we got 300,000 points for that, William. Let's do some type 1, type 2 error and talk over the problems. There's some really good ones on the quiz. So William just going out and being like, well, I'm just gonna go learn it. Congratulations, William. That's really awesome right there. And I'm really proud of you for that. For the Stats 1 project, how do we connect our data to a company? For example, I just went to use student data, but it says these questions for, yeah, you can just say like, you're a company, you said, like, you can just say you're analyzing UT students. Maybe you're trying to market something to them or something, you know? A quick question that I totally feel like I forgot, I don't remember. How do we know which p-value to use when doing regression on the project? Oh, yeah. Well, so which one are you doing? Oh, regression. Yeah. Let's talk about that. Regression p-values. Sure, yes. I thought you were doing a 2-sample t-test or something. Interesting. I can do some stuff. I'm opening the Apple Store data. And let's look right. Well, this one doesn't have enough. We can go to the bike data. All right. So let's talk about regression and how to look at p-values. Make sure I got the video details for today's video right here. And let's do that. Office hours, here we are. Let's go look at edit video. And okay, here we are. We are at 423 Stat 201 project. P-values in regression. Here we go. Let's check it out, Jennifer. Let's do it. Okay, so we're going to talk about the p-values in regression and how they work. If you notice right here, we've got some data. You won't have this data for the project. You'll have different data. We're going to do a regression by doing analyze, fit y by x. Now, why am I selecting certain variables like the way they are? Like this variable here, average temp, and then y is the other variable. Look at the two variables and tell me, why will I get regression? Which is a good review for the final. The final has what's called tools and techniques. Close. William, I think you're saying it, William. And William's got it right there. William, more points in the chat. We've totally broken the point scale. Now that people come to office hours are just totally decimating the points. So we'll start with some 10,000 points. That's our base points nowadays. 100,000 is amazing work. 10,000 is base points. Brian messes with the hair. Everyone gets points. So it's getting crazy long these days. So QQ is the first condition for regression. If you look down there in the corner, it actually shows you what you get if you put in different things. Like you can see the contingency table for 2 categorical variables. I'll raise it up a tiny bit. But notice how if you do the combination of red and red, you get this. Logistic is a categorical Y with quantitative. I know, right? Well, I change the point scales every semester. It's still like 1.3 points. But then everyone, it's like I try to encourage people to keep answering. And then it used to be you had to like email me and stuff, but now I just press a button. But I got to redo the buttons. I think the buttons are, no, buttons are working. There it is right there. So the buttons don't have enough points. Like I could press every button here and give you points, and it's not enough points. So I totally broke the point scale. Because people get excited when you give like 100,000 points. But I gotta redo it. I'm always thinking of the best way to do this. William, if you have a suggestion, let me know. So there we go. We have our regression now, and there's the regression plot. This is pretty good. I only see one issue, which will show up in another plot. So the points have inflation. Oh, the points have tons of inflation. So what issue is there probably going to be with this plot? What do you think is going to be the issue right here? What is going to be the issue? We're kind of just doing all regression just to review it. 6 million, my gosh. Bring back long hair, Brian Lowell. I reset the scales after the semester. The goal is everyone gets to the max. If you show up, you should get to the max. Plot thickens, yep. At the start, it's a little thinner. It starts to get thicker. We'll make a residual plot right here to take a look at what's going on. QQ straight enough, no outliers, plot doesn't thicken are the conditions. QQ means two quantitative variables. Straight enough means a straight line goes through the data. There's the line. Ooh, got a little, notice how the line, ooh, and the reason the line should go through the middle of the data, and at the start it's above it. There's a little linearity issue. There's a little linearity. Advanced way of checking this. The advanced way of checking this is with a lack of fit test. This is beyond Stat 201 at this point. Is a little bit of nonlinearity. And what's going to happen here, this is beyond 201, so if you want, don't listen to this. But if you really want to see if it's linear or not linear, we can do what's called a lack of fit test on the line. The null hypothesis is that there is no lack of fit, and the p-value, I guess, is going to be small. And there, ooh, it's barely small. So what do we do to the null that there is no lack of fit? Just barely. Wow, just barely. With this p-value right here that I'm pointing at, this is not the p-value for the regression, this is beyond 201. What would you do to the null? You should know that from 201. What do you do to the null? And look how Jump made it red with a star. Because look at the p-value. So this p-value right here, what do we do to the null? I thought it'd be lower, actually. We reject the null. And the null for the lack of fit test is that there is no lack of fit. So you're saying you have evidence of what? If you reject that there is no lack of fit, you are saying I have evidence there is a what of the line fitting the data properly. So think about how this is a lack of fit test with the null that there is not a lack of fit. So the alternative would be that there is a lack of fit, that there's a problem fitting the line, that this doesn't fit well. Same thing works when we fit normal distributions. The null is that the normal is a good fit. So the null for this is it's a fit test. We're fitting the line. Is the line a good fit? Null is that it's a good fit. Alternative is that it's a bad fit. And so we have evidence that it's a bad fit. It's beyond 201. Don't use that p-value. It's usually closed off. Don't use that p-value. Ironically, this p-value right here, and I might raise it up so you can see it a little bit better. So I'll zoom in here. This p-value right here is actually the p-value of the regression in the simple world, because this p-value down here is the p-value of the slope. So Jennifer, to answer your question very, very specifically, that p-value right there, not this one. What is this the p-value for? Read over to the left. This is the p-value of the what? So what is that one over above right here for? That is the p-value for the what, which is basically the same as the other one. We can find out more exactly what it is, but the top one is the intercept. The intercept is just where it hits the y-axis. The slope is the x-y relationship. Now the ANOVA, which is an analysis of variance, is also looking at the r squared and such. You can actually calculate r squared from this. If you take, you can kind of half see it right now. The model explains 4 million, we'll just call that 4 million out of the 12 million. And 4 million out of the 12 million is basically a third. And that's why the r squared you see up at the top is basically a third. That's the reduction in the sums of squared error. That's the total sums of squared error. That's the remaining of the residuals. Stuff we don't do in 201. But if I teach, what I do is I teach these concepts, so I should know what everything is in the output totally, like the F being the ratio of on average what we get for the mean over the residuals not explaining. So there's the mean sums of squared errors. Just divide by the residuals. It's that number divided by that number, this number divided by 1, but there's only one. Anyways, I'm gonna stop talking advanced stats. With that said, that's the p-value right there, the bottom one. If you hover over it, you can see exactly what it is. So you do a little hover over it. You don't really need to. It's close to 0. You should probably quote it as less than this. You have to, it's so weird. Jump, why are you weird? Yeah, there we go. There's the p-value. 8.76 e to the negative 36. So like 0.0000876. Very, very small. And then we have the estimates of the coefficients, B0 estimate, B1 estimate, uncertainty in B0, uncertainty in B1, ratio of estimate to uncertainty, divide 2000 by 20 to 100, or 2020, 220, wow. And 137 divided by 10. Well, look at that, you just divide by that and you just move the decimals. So those are how those numbers are calculated. You'll interpret the slope. For each one unit increase in x, we expect y to increase by b1 on average. You'll interpret the intercept. When x is equal to 0, expect y to equal b0 on average, so that on there. And you'll interpret the r squared. Blank percent of the variation y is explained with the variation x. So when you think about this right here, kind of makes sense. Oh, Catherine, good to see you right there. And feel free to ask questions. We're going to do something different in a moment. Might do some chapter 16. Can anyone do the r squared right here? We'll throw out another 10,000 points. Can anyone do the r squared interpretation? You should know the R-squared interpretation for this. We're predicting demand from average temperature. And I'll show you what's so good about R-squared, and I'll do it really quickly right here. But I'll show you something really awesome about R-squared. Then we'll go to chapter 16. Because R-squared is an amazing concept. So you take R-squared right there, which is not correlation. I'll show you why it's not correlation in a moment, even more so. Then you times it by 100, because R-squared is a decimal to begin with, from 0 to 100. And then R-squared is interpreted when you multiply it by 100, giving you 31.6% of the variation in the y variable is explained by the variation in the x variable. So 31.6% of the variation in demand is explained by the variation in average temperature. R-squared adjusted is after we penalize ourselves for multiple variables in the model. We don't talk about that. Root mean squared error is typical miss the model makes. Mean of response is average of the y variable, and that's the amount of observations, which you can't see on the screen. But what's really cool about R-squared, and then we're going to do some chapter 16, is I can take a variable like day of the week and use day of the week to explain demand, and I can still perform an ANOVA over here, and I can look at the R-squared. The R-squared would say less than 1% of the variation in demand is explained by day of the week. Notice how I didn't use two quantitative variables. Once again, telling us that R-squared is not correlation. I mean, it can be derived from correlation between two quantitative variables, but the R-squared right here, it's not correlation because correlation is only two quantitative variables. But R-squared is the reduction in the sums of squared error in a y variable of interest. More complicated. You notice we still have the ANOVA down here, and the ANOVA has more in the error than it does have in the explained term. The F statistic is much smaller, and the p-value is not significant. So there's the p-value right here in ANOVA. It's telling us that day of the week, and you notice how it looks very similar across day of the week. Day of the week is not a good predictor variable for explaining demand. So there's not a lot of variation explained. I'll try other variables like whether or not it's a holiday. I think no rain will do it. We submit for the million. No! Whether, you know what's really cool though? Watch this. Analyze, fit model, demand. You can do what's called stepwise regression. And now, wait. There we go. So what I've done here is I've made a model and I let R pick the variables for me. And now my model explains 42.2% of the variation in demand. There's the residuals, they look a little bit better. And the variables inside the model are all statistically significant. They're all quantitative variables. We have none of those categorical variables, which would be indicator variables. But this is a multiple regression right here. That's a confidence interval for the mean, not the predictor, not the individuals. Looks pretty good, with a lot better linearity too. Is there a lack of fit on here? There's not. You can even do predictions with this, but this is what we do in kind of advanced analytics right here. If you know what you're doing, you can just click a few buttons and get a model made for yourself, and then you want to analyze what's going on with the data, the leverage plots, the influence, all that good stuff that we can do by knowing kind of what's going on. It's all checks to see if the model's good or not. So pretty good model right here, only 42%. I wish we could get a higher variation explained because we're just trying to predict demand of bikes. But this is where it goes with using R-squared, because now we have 42% of the variation by adding in more axes and taking it from a simple model to a multiple model. So anyways, if you like analytics, if you like these things, this is kind of the power of analytics, is being able to, take data and understand it and run models, and we can do all this in seconds. Last thing, and I wish we had done this, I'm gonna do this really, really quickly. One of my favorite things, trying to remember where it's at in jump, here it is. Partition models. We could take demand right here, and we could actually make a partition model here using a decision tree. And the decision tree is going to also have an R-squared also, and we could predict demand, and you notice average temperature is the first split, and it starts splitting the data. Now, if you want to go really crazy and you want to go to advanced analytics, because this is kind of modern analytics, relaunch analysis, we want to go down here to a boosted tree. That's where it gets crazy. Number of layers, 1,000. That's good right there. Max split. Learning rate. Let's go to slower learning. The shrinkage parameter. And let's run this right here. And now we have an R-squared of 90%. Is it overfit? That's the question I would ask. Well, we didn't do training and holdout. So for 474 students watching this, I'm guessing we're probably overfit now. And you have to know the idea of what overfit is. And that's another RMSE right there. I forget what they call it, RASE. It's error. That's all it is, everyone. It's error. Anyways, shall we do some chapter 16, Cameron? If you can't tell, I love stats. I love doing stats. That's what I do. I do stats. Only 43.6%, but we were able to get an R squared of 90%, but I fear we've done some overfitting for all the stats nerds watching. You do it too. All right, one last thing. No one has questions. If anyone says chapter 16, we'll do it. Validation portion. Let's go to a 40% validation portion. Okay. Now let's see how we do. Okay. Not the worst validation ever. Validation of 43, which is close to our model. But there we go. We got an R squared of 66.5 on the original data and a validation of 43.7. Decent, some overfitting. I mean, that's a pretty big drop, but I've seen negative R squared holdouts. Okay, R squared can be negative? Yeah. Cumulative validation. Any questions? It's so cool. I don't use Jump that much for advanced analytics. I usually do. I usually use R for it. So I'm usually doing this in a totally different thing. I don't usually see the output that Jump can do for this. But I understand the ideas. So understanding the ideas would let me, hey, nearest neighbors, bootstrap forest. Like bootstrap. Let's go to 20,000 trees in the forest. That's number of terms. I'm going to fewer terms. Is there a tune grid? There's a tune grid. Yeah, I mean we're not seeing it on the holdout sample. It shows to 474. We're getting a big drop from our training data to our holdout and R squared, which is just percent of variation explained, and RASE is just the RMSE, I believe. Jump calls it that in this output for some weird reason. Let's do some chapter 16, right? No one said anything for a while. Let me call that last 4 minutes there, tangent on advanced analytics. Tangent on advanced analytics. Chapter 16, William, you got it. All right, some review of chapter 16. No one was saying anything, so I'm like, I need to move on. Advanced analytics tangent. There we go. Your brain's roasted. If I choose Lululemon as my company and my gender is my cat variable, oh yeah, would choosing male as my success make sense? Yeah, that's awesome. Yeah, you want to make that your audience, so you want to know if half the people who responded are male. Yeah, you can do that. Don't worry, we're not going to be too critical on how you choose to do things. It's just if you understand what you're doing. Like you can, whatever company you want to do and for whatever reasons, as long as it's not like, I'm choosing male because reasons. Like, and then you don't state the reasons. Like we're pretty open to however you want to do it. So we're going to be like nice and be like, oh yeah, that's a good reason. Use the prompt for your company. All right. Where's my Christmas cup? I'm mad. I'm gonna go down and say, give me a Christmas cup. Another drink and a I'm kidding. Thank you, Starbucks. Good drink today. That's not praline today. Give me my Christmas cup. I wonder the impact of Christmas cups at Starbucks. Some people like complain about them. Or seasonal cups, I guess. I don't know. It's weird that people like, I mean, if you don't like what a company does, my thoughts are always just don't go to it. Just you know, you don't like the cup a company gave you. I like this cup. It's got a good cup holder on it. It's good. It's a good drink. That's what matters most. You could always pour the drink in another cup. W take, Brian. Well, thank you very much. I don't know. It's just, there's a lot of things to get mad about these days. Like, I'd say just how the world treats some people. Like, a lot of things to get mad about, then a lot of things to not get mad about. No worries. Thank you for being here, Carrington and Cameron. It's a good drink. And now let's go over here and talk about some chapter 16. No one liked my green beans in class. I'm glad I got some other W takes though. Chapter 1. Let's do the chapter 16 homework. Because that we can just do fully. People can watch that and watch the full homework version. I haven't done a full homework. Okay, chapter 16 homework fully completed. Go do it here. Yeah, I know, it's a lot of just getting mad about stuff. It's not good for you to get mad. I mean, like, you need to do it, but other than that, just, you know, things are going okay, be okay. Which of the following are true? Explain briefly. A p-value of 0.01 means that the null hypothesis is false. That's not really how we talk about it. How do we decide to reject the null or not reject the null? Which I think it's saying, and I think I see the answer now. But how do we decide to reject the null or not reject the null? It's in the notes. So there's a little bar we have. Do I still have notes open from last time? There's a little bar. Cat named Quan is never going away. The little bar we have. Look at alpha, exactly. So you have this bar, alpha. And alpha is just the point at which you reject the null. If p-value is below, then you reject. If p-value is above, you do not reject. So you don't really say the null is false. You just have evidence against the null. You either reject the null or don't reject the null. A lot of people call that fail to reject when you're above alpha. I just say don't reject because fail to reject is just a weird thing. Think about this. If I say I failed to go to the mall today, what do you think I did? Like, it's tonight, and I'm like, you're like, did you go to the mall? And I'm like, oh, I failed to go to the mall. What do you think I'm trying to tell you? Like in normal people talk. If I say I failed to go to the mall. If I say I failed, you're like, did you go to the mall? And I say I failed to go to the mall. I failed to go to the mall. Well, so I didn't do it, right? I didn't do it. I did not do that. So failed to do something means you just didn't do it. So if you reject the null, you rejected the null. If you fail to reject the null, you didn't reject the null. So it's same lingo, but don't use the bad A word. It does not mean accept. Like I accept I went to the mall. No, I went to the mall or I didn't go to the mall. So false, whether p-value provides evidence against the null depends on the alpha. That should be right there. Provides evidence against the null, but it didn't show us. So this is interesting. The p-value provides evidence against the null, but it does not show it's false. That's kind of, and so if you've already clicked, I'm very sorry about that, but we don't show the null is false. We just have evidence against it. So they're kind of blending two topics right here. And when we have evidence, I failed to fail. This p-value provides evidence against the null, but it doesn't show it's false. That's true. And do we have sufficient evidence is the alpha? Just the way that's worded, because really we should know the alpha, but we don't really say the null is false. We say we reject or not reject. So when we reject, we have enough evidence against the null. A little tricky, my Pearson. You're not going to catch me today. A p-value 0.01 means the null hypothesis has a 0.01 chance of being true. No. The p-value is a conditional probability, which when we think about it, the p-value kind of helps you if you memorize this, but it's just a big phrase. The p-value is the probability, right as I say it, a p-value is the probability of our results or results more extreme occurring by random chance variation given the null is true. So it's a conditional probability. Given the null is true is the end of it, which is very important. So if Brian is a 4-minute mile runner, what should Brian do? Very quickly, run a what? If Brian is a 4-minute mile runner, what should Brian do? If Brian is a 4-minute mile runner, what should he do? Run a what? Like you would expect him to do what? I'm saying my average mile time is equal to 4 minutes. Then you'd expect me to run a 4-minute mile. You'd be like, oh, go do it, run a 4-minute mile. You say you can do that on average, well, go do it. But then if I ran a 4-minute and 1-second mile, which we'll pretend is here, we haven't calculated it, but we'll pretend we calculated it, then the p-value for the alternative that it takes me more time would be this. So there's the p-value shaded, and because it's a probability, and our result is the line. And the more extreme is because we're shading to the greater than side of this. So to the greater than 4. So more extreme is because of the right arrow. And the random chance variation is the normal curve. Given the null is true is the center of the curve right here where we put the most likely values. So the probability of Brian, we'll pretend the p-value, we're just making up a value for this. We'll say it's 40%. And we already got a 4 on the screen. We'll say it's 37%. That's the percent of curved shade right there. So if Brian is a 4-minute mile runner, then his time right here that we saw him run a mile in, he only ran one, so the average of it, we'll say 4 minute, 1 second. If Brian is a 4-minute mile runner, then this time we saw him do the mile in would occur by random chance or a time more extreme than it 37% of the time. So was this a likely thing for Brian to do if he's a 4-minute mile runner or an unlikely thing for Brian to do? His 4-minute and 1 second time was a likely occurrence given Brian is a 4-minute mile runner, or is 4 minute and 1 second time was an unlikely occurrence? Was it likely or unlikely by random chance? If Brian is a 4 minute mile runner, this observation right here would occur about 37% of the time, then this is a likely result. So think about that. You see me run a 4 minute and 1 second mile, just think what you would do in your head, and I told you I'm a 4 minute mile runner. Would you be like, you're a liar? Would you be like, okay, I still kind of believe you. I didn't run exactly 4 minutes, remember. I said I could do 4 minute miles, but I didn't quite do 4 minutes. Would you believe me or not believe me? Would you believe me or not believe me? You'd still believe me, right? And that means you would not reject the null. Now, you're not saying the null is true. You're not saying Brian's a 4 minute mile runner. You're just saying, I don't have evidence to go against him. And there's no real practical significance between 4 and 401, right? It's basically the same. And or even if you rejected the null, you might say there's no practical significance, but the p-value is very high, so we don't reject the null. You don't have enough evidence to say that I am higher than 4 minutes. But imagine if it took me 5 minutes to run the mile. So now we'd be further away. So our result over here is going to be much, much further away. So if it took me 5 minutes to run the mile, so if I ran my mile times in 5 minutes, I'm going to land all the way over here. And landing all the way over there makes a very, very what p-value. So there's the observed result, and the results more extreme are shaded to the right. So this is a very, very what p-value now. We can describe it as like 0.00001. I'm running a 5 minute mile, I'll be happy. But now it's like a 1 in 10,000 chance. So now you're saying Brian running a 5 minute miles, given he is a 4 minute mile runner, seems very unlikely by random chance. I reject the null that he's a 4 minute mile runner. I have evidence it takes him more than 4 minutes. But you could be wrong, which we'll get into later in this chapter. You could be wrong because maybe I was injured, or maybe I was just taking it easy, and maybe you made a type 1 error here. The type 1 error is when the null is true and we reject it. So you could have made a type 1 error and rejected the true null. Even I got to double check before I say something really quickly. But you could have made a type 1 error and rejected the null when you shouldn't have. So going back to the question right here, it means that the null hypothesis has a 0.01 chance occurring. No. The p-value is not the probability that the null is true. I wish they went into more detail. It's a conditional probability of seeing our results given the null is true. It's not a probability the null is true. It's the probability of our results given the null is true. So it's conditional. Choose the correct answer below. A p-value of 0.01 is evidence against the null. I mean, kind of. We already mentioned this earlier. It depends on the alpha, but it's kind of true. I mean, oh, really? Wait. A p-value of 0.01 is evidence against the null. Oh, they want to say it's evidence for the alternative. Ugh. Oh my gosh. The p-value proves... No, it doesn't prove anything. The p-value provides evidence for the p-value... Wait. How did I misread this? The p-value provides evidence for the null. No, it does not. The p-value proves... We don't prove things in statistics. So they're saying true right here. Whether p-value provides evidence, sufficient evidence, we could say. I do not like that answer. I'm glad this is multiple choice, multiple attempt. I would say a p-value of 0.01 is often sufficient evidence when using an alpha of 0.05. So whether a p-value provides evidence for the null depends on the alpha level. Why is that not the right answer? Like sufficient evidence. I guess, I mean, 0.01 is always evidence, but is it sufficient to reject the null? That's tricky. Choose the correct answer below. A p-value of 0.01 means we should definitely reject the null. Now they're going to mention alpha. Now they're just going to alpha right there. It's a good question. These concepts you should know really well, but the wording's a little sus wording. Whether a p-value provides sufficient evidence. Like when do we reject the null? P-value less than alpha. Low p-values are evidence against the null or evidence for the alternative. So you should reject the null when the p-value is low. But when do you reject the null? P-value less than alpha. So good concepts to know. Make sure to listen into what we said right here with the alpha level being the point at which you reject. That's what you want to make sure to understand concepts like this, that alpha is the point at which you reject. And you would say the lower the p-value, the more evidence you have. And when do you have sufficient evidence? When p-value less than alpha. Reject the null. Question number 2. How are people doing today? Question 1. 31. We'll get through the full homework. Statue 1. Chapter 16. Homework. Question 1, 2. Okay, well, I like these. These are fun ones. Which of the following are true? Briefly explain. Using an alpha of 0.05, a p-value of 0.04 results in rejecting the null. What do you think? You have an alpha of 0.05, you get a p-value of 0.04, you reject the null. Don't even read their answers. Boom, true. P-value less than alpha, reject null. Done. The alpha level depends on the sample size. You went to last class. Did we say anything about sample size telling you alpha? No. The researcher picks it. The researcher decides alpha, and in most instances, you will use alpha what? So the researcher picks the alpha, they decide on it, they decide at what level they're going to reject the null, and in most instances, 0.05, unless otherwise stated, 0.05. You can change it. Watch out. We'll talk more about what it can impact. It's type 1 error. So you pick it. Yeah, you just pick it. Should just say researcher picks it. With an alpha of 0.01, a p-value of this results in rejecting the null. If you have an alpha of 0.01, which is the point at which you reject, you get a p-value of 0.07. What would you do? Don't even read their answers. Don't, because if you know the answer, state the answer first, but don't read their answers. Then we'll find the answer that corresponds to what we think it is. No, you fail to reject. Boom. P-value above alpha, fail to reject the null. So because a p-value greater than alpha indicate no, it doesn't indicate the null is true. P-value greater than alpha results in no. Only a p-value less than alpha results in rejecting the null. Yeah. Notice how they didn't even say fail to reject. I wish they did, but only a p-value less than alpha results in rejecting the null. Greater at or greater than alpha results in not rejecting. This means the null is true. If you have a high p-value, it means the null is true. Is that what it means? Because we can make errors, remember. If the p-value 0.08 is above the alpha level 0.05, that means the null is true. All it means is you what? If the p-value is above alpha, all you did was what? It's not saying the null is true, because you can make errors, or you could just raise your alpha and reject the null. So a p-value greater than alpha does not mean the null is true. It means you don't reject, and we don't have evidence for the alternative. So the statement is false because p-value greater than the alpha level only indicates that there is enough evidence. No, you don't. Please don't tell me they chose accept. This statement is false because p-value greater than alpha only indicates that there's not enough evidence to reject the null. Boom. Notice how this one even says like the accept word, which I'm so glad that that's a wrong answer because we don't want to say that accept word. Really, I'll get mad if accept is in here anywhere. We don't accept the null. We either reject or don't reject the null. So really good question there. My Pearson coming back strong right here with some good questions. Rocking and rolling. Question 3, here we go. It is better to use an alpha of 0.05 than an alpha of 0.01. Did I ever say anything about better alphas? I mean, I never say anything about better. So it's better to use an alpha? No. No. You don't say, okay. The answer is obviously going to be this one right here because there's no better alpha. There's generally we use 0.05. Now what you have right here is alpha is going to impact type 1 and type 2 error. That's because alpha is type 1 error. So if you increase alpha, so this might make sense because at the very end of class I wrote the following. We'll probably resource this in a moment. I wrote the numbers 1, 2, A, B, and plus, minus. Alpha is what? Alpha is what? Like whatever you set alpha to, that is your rate of this that will occur. It is type 1 errors. Alpha is your type 1 errors. Alpha also does impact beta. The 3 things that impact beta, we'll probably need this here in a moment. Beta is impacted by alpha. I'll draw it as the right alpha. And then we'll do the little alpha symbol next to it. Also sample size and effect size. So William, you've seen these, right? And if these increase, they will decrease beta. Right, yeah, right, beta right here. Beta, which is this right here, which is type 2 error. And what they then increase is power, I need to, which is 1 minus beta. So this is a big thing to know right here and to be able to draw out. So power is the ability to correctly reject the false null. So if I take a larger sample, follow the arrows, what happens to power of a test? If I increase my sample size, what happens to power? If I increase my sample size, the test will be more or less powerful. If I increase my sample size, the test will be more or less powerful. It'll be more powerful. If I increase my alpha, which means have a higher type 1 error rate, if I increase my alpha, the test will be what? If I increase my alpha, it'll be more powerful. The problem, though, is increasing alpha gives you more type 1 errors. Imagine you wanted to find everybody who's sick. A type 1 error is a false positive, right? So a false positive would mean going up to someone who is what and telling them they're what. If you're trying to find someone who's sick and you do a false positive, what would a false positive mean? You go up to someone and you say they're what, but they're actually what? A false positive here. And this will set us up for success for a lot of questions to come here. False positive would mean what in this instance? If you have a false positive when you're trying to detect someone who's sick, you say they're sick and they're actually not sick. That's a false positive. But if you say everyone's sick, wouldn't you find everyone who's sick? Does that make sense? If you're like, everyone's sick, you would actually find everyone who's sick via false positives. You'd have tons of false positives, but you'd also find all the sick people. But that wouldn't be really useful because you have so much error. So the problem is how much error do you want? Because if you increase the error, you find more sick people, but you also find more people who you say are sick who are not actually sick. Now, a type 2 error is a false negative where you say someone's not sick and then they actually are sick. So if you decrease alpha and put a really high standard, I know I'm lowering my hands, but now you need tons of evidence to say that someone's sick. If you decrease the alpha, then you would have more type 2 errors where you say people are not sick because you don't have enough evidence, but they actually are sick. So it's a trade-off between type 1 and type 2 errors, where if you increase type 1, you lower type 2. If you decrease type 1, you increase type 2. And that's exemplified over here in the following graphic, that type 1 and type 2 error are inversely related here by the different color arrows. But the thing about power is as 1 minus type 2 error. So it's the complement of type 2 error. So if you increase alpha, which decreases beta, you actually increase power, which is the ability to reject the false null. Actually, I call it the ability to find results. You should basically say that in statistics. It makes more sense. Like you can find more sick people if you just say everyone's sick, which is more type 1 errors. So going back here to the question, we see right here a lower alpha lowers type 1 because alpha is type 1, but will increase type 2 because if you decrease type 1, you increase type 2. And they're lowering alpha by bringing alpha from 0.05 to 0.01. So very clearly that. And that says I'm wrong. That'd be funny. If we use an alpha of 0.01, then a p-value of 0.001 is statistically significant. Yes or no? This should be very easy right here. A p-value of 0.001 is statistically significant with an alpha of 0.01. Alpha is the bar at which you say things are statistically significant. 0.01 is the bar. P-value 0.001. So when the p-value is low, what do we do? The p-value is low, reject the null, so it is statistically significant. That is as true could be. Yep, reject the null. If we use an alpha of 0.01, then we reject the null hypothesis. Not the same thing. If we use an alpha of 0.01, then we reject the null if the p-value is, yeah, it's just different wording, right? They're trying to trick me here. If a p-value is 0.01, we reject the null hypothesis for any alpha level greater than. That makes sense too, right? Yeah. Set your alpha, I mean, don't do that. Don't set your alpha after doing it. But if the alpha was higher than 0.01, you reject the null because then your alpha is greater than your p-value. Or p-value less than alpha is usually the way we like to refer to it. So you look at the p-value, is it less than alpha? Makes sense. Little tricky wording and interesting they chose all trues right there at the end. But that's got that. Really easy one here next. What is the name of the threshold? Drop it in the chat right there real quick. What is the name of the threshold by which we reject the null? What is the name of the threshold by which we reject the null? Don't even look at their answers, remember. It is simply alpha. Yep, significance level alpha. So the threshold, if a p-value is smaller than the level of significance, what do we reach? So p-value less than alpha. So if the p-value is less than alpha, what do? Don't read their answers. Reject the null. P-value less than alpha, reject the null. I'm trying to put these in here. What is the probability the test correctly rejects the null? As I said, I set us up for success if you're watching through this video. What is the probability of correctly rejecting the false null? That's the textbook definition of the term we're talking about. The probability of correctly rejecting the false null. So the probability of correctly rejecting the false null is power. What is the formula for power? That is power right there. Well, it even says it on the screen now. Formula for power is 1 minus beta, where beta is the probability of a type 2 error. So then you have to think about what impacts beta, which we'll talk about today in class. And we've just done a little review today during office hours. Once again, thank you to everyone who watches office hours either in the future. I've gotten emails from students be like, hey, I watch office hours. Can you help me with this? Yeah, definitely. So thank you if you're watching this. Got an email this morning, help a student with a project. And I'm hoping they I told them between 100 to 108. So shout out to you if you're watching. Really appreciate that. And I want you to get some great grades there. So try to respond to everyone as quickly as I can. What is the name of the difference between the value in the null and the population parameter? Now, you might know this, or you might not. I haven't mentioned it. I did mention it today, but I didn't tell you because I was like, ooh, it's a bigger topic for the moment. So what this is this is effect size. And won't say it in the chat yet. Someone's probably going to say it in a half second. But this is what is called effect size. Because the effect size, it's effect size. Yeah, look, because critical value is the point at which we reject. The alpha level is the critical value is a t calculator. Excuse me when I misspoke right there. I don't really use critical values because you don't need to calculate them anymore. It's like an old school thing. Critical values are the t or z calculated by which beyond you reject the null. So it's based on your alpha, and then you calculate the critical value, the t or the z required to reject the null, and they see if your t or z is above the critical value. But you can just find your p-value. It's a quicker way. Just run it through jump, look at p-value. So typo and error is rejecting the true null when we shouldn't. And alpha level is the significance level we pick for the problem. And then the effect size is the true difference between the null and the population parameter. So like what I like to talk about here is people being sick and going to the hospital. If you think about a small effect size, it would be someone going to the hospital and being like, I'm sick. That's a small effect size. Because the null hypothesis is that they're healthy, and then maybe the truth right here is that they are sick, but it's a very small effect, right? But if someone goes to the hospital and they're on a stretcher and they're like, ah, and they're not doing well, that's a big effect size because the null is that they're healthy, and then the population parameter, let's say the truth, we don't know what the truth is, but we'll pretend for a moment we know that they're actually really sick, like they're not faking it or anything. The truth is that they're really sick, so you can see this big effect size. If I were to take me and my brother, or me and LeBron James and play basketball, where would be a bigger effect size where the null is that me and the other person are the same? If I play my brother in basketball or LeBron in basketball, when would there be a bigger effect size? The effect size is the difference between the null and the truth. The null is that I'm the same as my brother. The null is I'm the same as LeBron James. And then the effect size is the true difference. Now, you'll never really know it, but you could estimate it by watching us play. So what would be the bigger effect size? Because it's the difference between your null, that we are the same at basketball, and the truth, the population parameter, which is the difference, the actual true difference. When would there be a bigger effect size between Brian and his brother or Brian and LeBron? I think, maybe say it's the same. LeBron James right there. So this is effect size. Effect size is the difference between the null, which is what you start out believing, and the truth, which you don't really know, but you could look at and say, like, I think there's a bigger effect between Brian and LeBron because I'm seeing this big difference. Brian never scores on LeBron. He got 1 point on his brother in 21, but LeBron smoked him totally. Ooh, this is a good question. Here we go with some really big ones. Thank you, Cameron, right there. Let's throw you 100,000 for being here this whole time, answering these questions. Thank you, Cameron. Leading the way on the points. We'll see who leads at the end. It'll be pretty interesting. So, 2 more questions. 4 to 6. This one is pretty tricky. Catherine getting those points too. Chapter 16, homework. Question 8. Okay, let's do it. For each situation in parts A through D, state whether it's a type 1 or type 2 error or neither error has been made. The bank wants to know if enrollment on their website is above 30% based on a small sample of customers. They test the null that the true proportion of enrollment is 30% versus the alternative that the true proportion of enrollment is above 30% or greater than, and reject the null. Now, the only error you could make when rejecting the null is a what error. Let's narrow this down. Remember our sayings if you haven't heard this before. If only it was money. Good to see you, Patrick. In a type 1 error, the null is true, and we reject it. In a type 2 error, this is 2, the null is false, and we fail to reject it. Notice how there's 2 F's in the type 2 error. This is an F. Read it again. Try saying it out loud. Try doing this, because you could do this. If you do this on your test, and the teacher's like, what are you doing? Be like, Brian taught it to me. I'm just trying to remember how to say it. In a type 1 error, the null is true. That's a T, and we reject it. In a type 2 error, the null is false. That's an F, and we fail to reject it. 2 F's of the type 2 error. So knowing that, as Cameron said right there, if we reject the null, it can only be a type 1 error. They find out later that it's 28%, so they think they have evidence that it's greater than 30%. Turns out they were wrong. So since they were wrong, they did make a type 1 error. So they made a type 1 error. The actual is very close. They rejected the null, so they shouldn't have rejected the null. Wait, what? Did I move? The actual value is close to there, but they rejected the null. They made a type 1 error. Oh, the actual value is not greater than. Yeah, that's true. All right. Just the wording of it. Really? Let me see here. The actual value is close to. I mean, it is close to. They shouldn't have rejected the null. So it's not greater than. That is true. The actual value is not greater than 30%. That's just mean. Really? Type 1 error. They shouldn't have rejected the null. I mean, they should have actually rejected the null for another alternative, my Pearson. They should have found evidence it's less than. So they went the complete opposite way on it. So, ugh, kind of crazy. Patrick, yeah, I think former student, right? Because I see we should get you some U-Bucks again. A student tests 100 students to determine whether other students on her campus prefer soda brand A or soda brand B. Finds no evidence that preference for brand A is not 0.5. So they did not find evidence. If they did not find evidence, what did they do? Reject the null or not reject the null? So did they reject the null or not reject the null? They found no evidence. They didn't find evidence. Evidence for the alternative. But did they reject the null or not reject the null? Reject or fail to reject the null? What did they do? Their null is that there's no difference. They did not find evidence. So what did they do? They didn't reject the null. Oh, I think I just said it. They failed to reject. So the only error they could have possibly made is a what? Since they failed to reject, the only error they could have possibly made is a what? So in a type 1 error, the null is true and we reject it. Like you have a true null and you rejected it because that's the error. You shouldn't reject a true null. And in a type 2 error, the null is false and we fail to reject it because you should reject the null when it is false. But a company comes in and finds no difference. So did they make the right choice? They didn't reject the null of no difference, and a company comes in and finds no difference. Did they make the right choice here? So they researched this and they said, I think there's no difference. I don't reject the null. And the company comes in and says, yeah, we don't find a difference either. So did they make the right choice? Did they make the right choice? So they did, because the company came to the same conclusion, so we have no evidence of an error yet. It's like they were like, I don't reject the null, and then company's like, yeah, we don't reject the null either. Like, okay, no error. A human resource analyst wants to know if the applicants this year score on average higher, so they're looking for evidence for mu greater than proposed score. Higher on the placement exam than 52.5, so mu greater than 52.5 is the alternative. The null is mu equals 52.5. She samples 50 scores and finds the average to be this, so she fails to reject the null, so she didn't have enough evidence, even though she found greater than, she failed to reject the null. At the end of the year, they find out that the mean was 55.3. What error was made here? So I'll let you figure it out. Then I'll choose right. It's type 2, yep. Because she didn't reject the null, so she could only make a type 2 error. And then she found out it was greater than, so the null was false. She should have rejected it. So this is a type 2 error, which is greater than, so we should be good right there. A pharmaceutical company tests whether a drug lifts the headache rate of 25% achieved by placebo. They failed to reject the null. So they only could make a type 2 here. The null hypothesis because the p-value is super duper high. Further testing shows that the drug actually relieves headaches at 38% of people choose the correct answer. So it's very clearly a type 2 error. They should have rejected the null. Yeah, that should, oh, there we go. Pretty good question. What type of error is made when a true null is rejected? There you go. And hopefully, so Cameron, what do you think now? Is it a bit easier? I hope we could do another one off the quiz or something, but type 1 and type 2, when you get it down, and I really believe in our saying, in a type 1 error, the null is true and you reject it. In a type 2 error, the null is false and you fail to reject it. Easiest way to memorize it. They've got some tables in some books, but I've never liked the tables. It's just practicing understanding what's going on right here. I'm trying to think if there's other major questions on this, but all in all, really, my Pearson's given me so many errors lately. We'll go over here and play a little music. Might have a friend swinging by today. Former classmate coming by the department. W. This is due on the 30th, so I need to put in the extra credits tonight for it. Oh my gosh, there's like a billion questions here. Or I did the bank one. Okay. We'll do at least one more right here. Three, bottom 3, that's all 1. Let's go check it out. Okay. For each of the following situations, state whether a type 1 or error, type 1A, A type 1, A type 2, or neither error was made. Okay. A test had the null of the proportion is equal to 0.8 with the alternative that it's less than 0.8. We failed to reject the null, so only a type 2 error could occur. Later it's discovered that the proportion was this. That is a type 2 error because they should have rejected the null. So the type 2 error because the null should have been rejected. There we go right there. That should be good. The test was done with the proportion is equal to this. The proportion is not equal to this. They rejected the null. Good, then they should have rejected it. So no error occurred. The null was rightfully rejected. So a lot of options. A test was ran with the mean is equal to this, with the mean greater than this. They reject the null. It's later discovered that's equal to this. They shouldn't have rejected. So when you reject the null and you shouldn't have, that is a type 1 error. Yeah, type 1 error occurred because the null should not have been rejected. So the null is that the proportion is equal to this. The alternative is that the proportion is less than this. They failed to reject the null. They should have rejected the null. The type 2 error occurred because the null should have been rejected. I think we did it. Really? Is it that one I saw back here? Nope. First one we did? Literally the first one. It is the first one. Let me read it again. A test occurred with this right here. She fails to reject the null. Later it is just... Oh! It's the alternative. That is a really ridiculous... I always miss live officers. Oh no, well, Mike, I made mistakes here now. Okay, so the problem is if she had rejected the null for this alternative, she would have found evidence it's less than. So the problem is the sign of her alternative, really, or whoever it is. So my Pearson actually hurts my eyes to look at the text. Yeah, same thing, Cameron. You can increase it if you hit Control plus. If you hit Control plus or Control minus, it'll increase, decrease font. Also open up in my Pearson. That is ridiculous. A major error occurred. because the problem here is if she had rejected the, why do I keep saying she? Is there, if they, I don't know who it is, if they had rejected the null, then they would have found evidence that's less than, but they shouldn't find evidence for that. So it makes sense that they didn't find evidence that it's less than that, but there should be evidence that it's greater than that. So if we had done a different alternative, we should have found evidence for it. So we kind of made a type 2 error by failing to reject the false null for the proper alternative. I just missed, I didn't see the sign by which he was doing it. Let's do another version of it and ace it here. Okay, so here's another version. Now she should have rejected the null. Notice how the truth is less than, so she should have evidence for that. This is a type 2 error. The null should have been rejected here. This one, she rejects the null. They reject the null. Later it's discovered that it is this, so that is good. No error occurred. The null was rightfully rejected. Rightfully rejected, I said, come on. And so proportion is equal to this, proportion is not less than this. They failed to reject the null. Good, that's the trick one there again, because they shouldn't reject the null. So no error occurred. The null was rightfully not rejected. They're trying to find evidence that's greater than this. Later they discover they reject the null, so this is a type 1 error. The null should not have been rejected. Should not have been good. This is tricky. I picked a good tricky one here. I'll do it one more time just to make sure. But this is tricky. Good tricky one, but okay, the null is that the proportion is equal to 30%. The alternative we're looking for is less than 30%. They failed to reject the null. Good, they shouldn't have done that then, because if they rejected the null, they would have found evidence in the wrong direction. No error occurred because the null was rightfully not rejected. They believe that it's 70% the proportion. They're looking for evidence. It is not equal to that. They reject the null. Later they find out it is that, so no error occurred. The null was rightfully rejected. Right here, we believe the mean is 25. We're looking for evidence that's greater than. Later it's discovered is 24.9. So this was a type 1 error because the null should not have been rejected. Type 1 error because the null should not have been rejected. Type 1 error because the null should not have been rejected. They're testing the proportion is equal to 80%. They're looking for evidence less than 80%. They failed to reject the null. This is a type 2 error because they should have rejected the null. They should have found evidence for that. Type 2 error because the null should have been rejected. Only that first one got me because the alternative, if it was in the other direction, would have been a type 1. So tricky with this one right here. This is the one that really could catch people, because if you were to reject the null, you'd have evidence in the wrong direction. So if you're looking for evidence in that direction, you shouldn't reject the null. That's the proper choice to be made. But in truth, the null should be rejected, but for another alternative. But the thing is we don't have evidence that's less than. We would have evidence that's greater than for question A right there. So really good stuff. I'm going to take a quick break, see if my friend's here. Until then, bye for now, everyone. Bye, bye, camera, bye, everyone.